All right, so in this video, we're going to go through two quick corollaries of the mean value theorem, which basically tell us that any two antiderivatives of a function differ by a constant. So this is a familiar thing from calculus, right? The reason when you integrate something, if you take the indefinite integral of a function, you write something, something, something plus c, right? And the plus c is there to indicate that there are many different functions whose derivative might be the original function you were given, but they all differ by a constant, right? And so it turns out we can actually obtain this result, not phrased in terms of integrals, obviously, because we don't really know what integrals are, but antiderivatives are something that you can talk about without knowing what integrals are. And then it's actually just the fundamental theorem of calculus that tells you that the antiderivative, that the integral of a function is the antiderivative. But an antiderivative, right? So given a function f on, a, b, an antiderivative of f is a function f such that f is differentiable on a b and f is differentiable on a b and f prime equals f on a b. So they have the same values, right? So our first corollary here, so we don't need integration at all yet to talk about antiderivatives. So although these aren't phrased, so this is don't take this as like a really rigid definition, because this definition isn't even given in the book anyway. And I'm just using it here to kind of illustrate, how you can build a language around antiderivatives that doesn't involve integrals, right? But yeah, so corollary 29.4, if f is differentiable on a b and f prime of x equals 0 for all x in a b, then f is constant on a b. Okay, so suppose there were, x1 and x2 in AB such that f of x1 is not equal to f of x2. Then the mean value theorem, right? And again, when we do this, we're technically applying the mean value theorem to the restriction of the function to the closed interval x1, x2, or like in the lecture question from last time, we're technically applying the mean value theorem to a restriction in that case too, but we're going to do that all the time. So you don't have to always every time say okay, let's use the restriction or whatever. Just in the back of your mind, that's kind of what's going on, right? So the mean value theorem tells us that between x1 and x2, there exists a point where f prime equals whatever the average slope is. So so there exists a x, right, in x1, x2, such that f prime of x equals f of x1, or sorry, f of x2 minus f of x1 over x2 minus x1, which is not equal to 0, contradicting the assumption. So that's the argument here. So notice that we're kind of using something we know about the derivative. We're using a statement that we know to be true about the derivative on all of the on the entire interval to conclude something about the values of the function itself. We're doing that via the mean value theorem. That's going to be like a recurring pattern of like how you use the mean value theorem is like when you know something is true about the derivative on like the entire interval, then you can apply the mean value theorem and conclude something about like pairs of points. Conclude something about like pairs of values of f, basically. Yeah. So anyway, yeah, that's that corollary. So then as a second corollary here, to kind of generalize this to corollary to arbitrary like antiderivatives basically. So suppose f and g are differentiable on AB and f prime equals g prime on AB, then there exists a C such that f prime equals, or sorry, such that f equals g plus C on AB. Okay, so this is so basically this is saying that f and g are antiderivatives of the same function. Right, so we're just saying that basically any two antiderivatives of a function differ by a constant, right? So that's why we use the plus C when we take indefinite integrals, is that that represents like all of the possible antiderivatives of the function that we started with, because any two of them only differ by a constant. So the proof would just be, the proof is very, very simple. Apply the previous corollary to f minus g. Okay, because f minus g, if f prime equals g prime on AB, then the derivative of f minus g is 0 on AB, right? So f minus g prime is 0 on AB. So f minus g equals some constant. Right. So yeah, there you go. So once we have the fundamental theorem of calculus, this here will tell us that if any two that basically that if you take the indefinite integral of a function, that all the possible candidates for the indefinite integral are differ by constants. Yeah. So that's all for this section. In the next one, we'll talk about increasing and decreasing functions.